So in this section, we're going to show how to estimate hazard ratios for groups, comparing groups who differ in more than one predictor value using the results of multiple Cox regression models. So after viewing this section, you will be able to estimate a hazard ratio comparing the hazard of a time to event outcome for two groups who differ in more than one predictor value. So let's first look at the example with the primary biliary cirrhosis trial. We're going to use the results from model 2 here, which was the model that included 4 predictors in it: treatment, whether a person was randomized to the DPCA or placebo group, their age put into quartiles, classified into one of 4 quartiles, their bilirubin levels, which was in milligrams per deciliter, and the sex, which was females versus males, where males were the reference group. If we were to write this out on the regression scale, and you can take this as a given, but you could have gotten this by taking, for each predictor to get its respective slope, taking the natural log of the adjusted hazard ratios presented in that column from model 2. So for example, the adjusted hazard ratio for treatment compared to placebo after adjusting for the other predictors was 1.10. The natural log of that is 0.10. And similarly, you could take the natural log of the adjusted hazard ratios for each of the other predictors to get these slopes. So let's estimate the hazard ratio mortality for 60-year-old males in the drug group on DPCA with bilirubin equal to 1 compared to 40-year-old females on the placebo arm with bilirubin equal to 0.5 milligrams per deciliter. So if we were to write out the log hazard for each of these groups in terms of the regression results, we would do it simply by substituting the appropriate x values for each group into the equation and seeing what fell out. So for the first group, they are in the DPCA group. So their value for treatment, or x1, is 1. They're in the 4th age quartile. So their indicator is the x4 is equal to 1, and the other 2 are zeros. Their bilirubin is 1, so their x5 value is 1. And they are male in the reference group for sex, so their value for sex, or x6, is 0. So at any given time, we would start, to get the log hazard for this group, we would start with our intercept evaluated at that time, and then add 0.1 times 1 for the treatment component, 0.87 times 1 for the age component, and add 0.15 times 1 for the bilirubin component. And what we'd end up with, to get the log hazard at a specific time, we would have to find out what the intercept evaluated at that time was, take that value and add 1.12 to it, which is the sum of 0.1 plus 0.87 plus 0.15. If we were to do the same thing for the second group of 40-year-old females and substitute in their appropriate x values, so they're on the DPCA group in the reference group, so they get nothing added for treatment. They have bilirubin levels of 0.5, so we take the slope for bilirubin of 0.15 and multiply it by 0.5. They are in the reference group for age, and then we add in the difference for females to males, since this group is female, the slope for sex at negative 0.52 times 1. This is what we'd add to whatever the starting point was for any specific time where we were estimating the log hazard. So we take the intercept evaluated at a specific time and add negative 0.445 to get the log hazard at any time for this group. And negative 0.445 is the sum of these two pieces here. They come from the slopes and x's. So if we were to take the difference in this at a specific time, as long as we're comparing the two groups at the same time in the follow-up period, the difference in their log hazards would be 1.2 minus negative 0.445. And that difference is equal on the difference in log hazards, or the log hazard ratio, is 1.565. So if the log hazard ratio estimate is 1.565, to estimate the hazard ratio, we'd exponentiate that. And e to the 1.565 is equal to 4.78 approximately. So the first group is older, it's on the treatment, has higher bilirubin, and is male. The cumulative impact of those two things compared to the differences for the other group, who is younger and female on the placebo group with lower bilirubin, is an estimated hazard ratio of 4.78. It's not easy to do, but using a computer you could get a 95% confidence interval for this, and really what's the difficulty of this is getting the standard error, because this is a function of the respective combination of slopes and x's that come in this comparison, and the standard error would be a function of that. But the resulting confidence interval, I just want you to know that they can be computed for these things where we're comparing more than two groups, is 2.3 to 10.0. So I just want to show you something when it comes to taking differences. On the log scale, we've done this before, but it's worth showing again in the context of multiple Cox regression. If we were to look at this difference in log hazards piecewise and keep each individual component represented, the intercept, of course, would cancel between these two groups. The difference that comes from being in the different treatment groups would come from the difference in treatments times the slope for treatment. It's binary, so the first group was a 1 because they were in the DPCA group. The second group is a 0 because they were in the placebo, so this is the part of the overall difference in log hazards that comes from the treatment difference. The part that comes from age is 0.87 we add to the first group because they're in the oldest age quartile, minus 0 for the second group because they're in the reference quartile. The difference that comes from bilirubin differences comes from the slope of bilirubin, 0.15, times the difference in bilirubin values, 1 minus 0.5. And then the difference that comes from sex is the 0 for the first group because they are males, minus the portion, the negative 0.52, that comes from being female for the second group. So if we write this out piecewise and then we exponentiate this sum, so we go through this, we exponentiate the sum, we keep that difference we saw before in its sum form and look at each individual component piece, we get e to the 0.10 times e to the 0.87 times e to the 0.15 times 5 times e to the 0.52 because the negative 0.52 becomes a plus. If we rewrite this out with the exponentiated versions, this is the adjusted hazard ratio for treatment from that table. This is the adjusted hazard ratio for age quartile 4 versus the reference. This is the adjusted hazard ratio for bilirubin per 1 unit difference, and this gets raised to the difference in values for the two groups we're comparing, the 0.5 power, and then this is 1 over the adjusted hazard ratio for sex because that was given in the direction of females to males, but the groups we're comparing are in the opposite direction. If you multiply these out, you get the same thing that you did before when we added this all up and got the overall difference and exponentiated that. So you can do this piecewise by multiplying the appropriate portions on the hazard ratio scale, if you wish, instead of taking it back to the log scale, doing the math, and then re-exponentiating. So let's look at that approach for predictors of infant mortality. So let's refer to Model 3 here, where we had gestational age, treatment, sex, and maternal parity. Let's use those results to estimate the estimated hazard ratio mortality for preterm male children born to mother was randomized to receive vitamin A who had 5 previous children, compared to female children born at 40 weeks who were born to mothers randomized to receive beta-carotene who have no previous children. So you could go back to this and write the entire regression out on the log scale, like we did in the previous example, do the computations for these two groups on the log scale, take the difference in the estimated log hazards, and then exponentiate that. But you could just start on the adjusted hazard ratio scale as well, as we had shown at the end of the previous example when we exponentiated the pieces of the difference separately. So what we're comparing here on the numerator is preterm male children whose mothers were randomized to vitamin A group and mothers had 5 previous children, to a group of children who were 40 weeks gestation, who were female, whose mothers were randomized to beta-carotene and had no previous children. So if we look at this in terms of the pieces, there are the adjusted hazard ratios. The first part comes from comparing preterm children to 40-week gestation children. The second part compares male children to female children. The third piece is the part that has to do with vitamin A to beta-carotene, and then we multiply that by the fourth piece, which comes from the comparison of parity, 5 previous children compared to no previous children. And so if we do this based on the adjusted hazard ratios in that table as presented, and we don't have to take things back to the log scale as we showed before, the comparison that comes from gestational age is preterm to 40 weeks gestation. Well, the hazard ratio in the opposite direction for those 40 weeks gestation to preterm is 0.32. So we're comparing this in the opposite direction, preterm to 40 weeks. So we take the reciprocal, or 1 over that hazard ratio is given. For male children to female children, the estimated adjusted hazard ratio was simply 1. So we'll take that. For the vitamin A group compared to the beta carotene, well, the hazard ratio of vitamin A to the placebo was 1.04, and the hazard ratio of beta carotene to the placebo was 0.99. If we take the ratio of those two ratios, we'll get the adjusted hazard ratio for vitamin A compared to beta carotene. And then the 5 previous children, the no previous children part, is a hazard ratio of 0.79 to 1. If we multiply these together, this is the same result as if we did the computations on the log scale, where the differences are additive and exponentiate the overall difference. When we exponentiate something that's additive on the log scale, it becomes multiplicative on the exponentiated scale. So if you don't believe me, you can go back and do this on the log scale by writing out the Cox regression equation by taking the natural logs of the adjusted hazard ratio given in that results table, doing the math, getting the overall difference and exponentiate it, and you'll get the same result. An adjusted hazard ratio comparison for these two groups of 2.59. If you were to put a confidence interval in them, I guess I had to go to the computer to do this and get the standard error, and it's involved to some degree, but the 95% confidence interval is 1.77 to 3.98. So in summary, the results from multiple Cox regression can also be used to estimate hazard ratios comparing the hazard of the outcome for groups who differ by more than one predictor. These can be computed on the regression scale, they are a linear combination of slopes, and then transformed, or using the adjusted hazard ratios and multiplying and or dividing the adjusted hazard ratios given by those exponentiated slopes. Confidence intervals can be computed for each of the above quantities, but it is complicated. And I'm not saying you couldn't handle it, but it's just more involved in using the computer. And so I'm not going to focus on that here, but I do want you to know that these things can be estimated. Confidence intervals for differences, for hazard ratios, comparing groups who differ more than one X value can be computed as well.